Let's learn how to calculate the ideal mechanical advantage, the actual mechanical advantage, and the efficiency of simple machines. First of all, what is the IMA of this ramp? On your reference table, the IMA is equal to the effort distance over the resistance distance. Remember, the resistance is also called your load, and the effort is what you do. Which one is your effort? Well, how do you drag the weight up the ramp? Oh, this way. So 24 meters is the distance of your effort. That's how you use the ramp. 5 meters is the result of how your resistance or your load is lifted. It is lifted by 5 meters by using this ramp. Therefore, 5 is the resistance distance. Do your math and you'll get your answer. By the way, this tells you how many times easier it is to lift the load using the ramp rather than lifting it straight up. It has no units because meters and meters cancel. You try number 2. It's just like number 1. Number 3, what is the actual mechanical advantage of this ramp? When you look at your reference table, the actual mechanical advantage is the resistance force divided by the effort force. So here the effort was on top, here the effort is on bottom. Now remember, when you use a ramp, you drag it up the long part of the ramp. You don't just lift it up. So if you drag it up the ramp, it takes 15 newtons of force. That is your effort force. When you lift it straight up, that's the effect that the ramp had, and it's as if you lifted it up with 35 newtons of force. That's the resistance. Do your math, and you'll get the actual mechanical advantage. The difference between the ideal mechanical advantage and the actual is that the ideal assumes you have no friction. The length of each part of the ramp actually has nothing to do with the friction, so this will give you the ideal mechanical advantage. The force that you use is used to calculate actual mechanical advantage because you have to put in a little extra force to overcome friction versus if you lifted it straight up and had no friction. You try number 4, it's just like number 3. Number 5, determine the efficiency of a ramp where the work input is 20 joules and the work output is 18 joules. The formula for efficiency is found on your reference table. The efficiency is the work output divided by the work input times 100. Just make sure you do the work input and that goes on the bottom. That's the effort work. Then the output is what the machine does and the outcome, and that goes on the top. Yes, it looks like efficiency equals wout over win, but it's actually the work output over the work input. They tell you that the work input is 20 joules. That goes on the bottom. And the work output is 18 joules. That goes on the top. And don't forget to multiply times 100. People often forget to do that. When you get your answer, that is 90% efficiency for this particular machine. If you ever get an answer that's over 100%, something went wrong. In fact, if you get exactly 100%, something went wrong, because every machine has some friction and you'll never have 100% efficiency. Number 6, what is the efficiency of a motor when the work input is 2,000 joules and 1,250 joules is used to overcome friction while the rest is used to move the car? So there's the work input. That's easy. That goes on the bottom. But this isn't the work output. This is the work used to overcome friction. The rest of it's used to move the car, and that's the work output. So how much was put out? Oh, do 2,000 minus 1,250, and that will tell you how much work is actually used to move the car. Now, that's our work output. That goes on the top. Don't forget to times by 100, and you can do the math, and that is in percent. You try number 7 because it's just like number 6. Now let's find the ideal mechanical advantage of a lever. Here is your effort, and the load is your resistance. Here's the fulcrum. The ideal mechanical advantage is the distance of the effort from the fulcrum over the distance of the resistance from the fulcrum. It's always measured from the fulcrum, which in this case happens to be in the center. So, divide the effort distance, 37 meters, by the resistance distance, 12 meters, and you'll get your answer. Remember, there's no unit because meters cancel, and this tells you how many times easier it is to use this machine than just lift it normally. What class of lever is it? Remember, FRE, fulcrum, resistance, effort. The one that's in the middle tells you which class of lever you have. You should be able to do number 10. Now, what does it mean when an ideal mechanical advantage or actual mechanical advantage is greater than 1? That tells you that the machine makes it easier to lift. But what if the IMA or AMA is less than 1? That makes it harder to lift. So why would you want a machine that made it harder to lift? Well, there's usually a trade-off between force and distance. So if you're putting in more force, but only a little bit of distance, you're getting out a much greater distance, even though you're getting less force. For number 13, this is your resistance or your load, and this is your effort force. This is where you press down. The effort goes on the bottom, and the resistance goes on top. It turns out that if you just weighed this little mass, it's 327 newtons. So that's the force if you just plain lifted it without using a lever. Do your math, and you'll have your answer. Then do number 14, because it's the same as number 13. Number 15, calculate the ideal mechanical advantage of this lever if the effort force is 10 centimeters from the fulcrum and the load is 30 centimeters from the effort. Hint, always measure how far the effort and the load are from the fulcrum. Okay, what in the world does this mean? First, the effort force is 10 centimeters from the fulcrum. There's your effort, there's your fulcrum. So this distance here is 10 centimeters. Then, the load is 30 centimeters from the effort. There's your load, there's your effort. So this distance is 30 centimeters. But be careful. You must measure how far the effort is from the fulcrum. Okay, that's easy. And how far the load is from the fulcrum, not just from the middle. See, in these problems, the fulcrum happened to be already in the middle, so that was easy. But when this happens and the fulcrum is not in the middle, you must measure how far it is from the fulcrum, not how far from the middle. So our effort is 10 centimeters away from the fulcrum. That's 10. Our resistance, our load, is 30 plus 10 centimeters away, which is 40 centimeters. Now do your math, and you will have your answer. You try number 16 through 20. Number 21, what is the ideal mechanical advantage of this pulley? Hint, if there is no bottom pulley, only count the rope segment tied to the pulley. There's only a top pulley, none at the bottom. There is one rope segment tied to this pulley. Therefore, the ideal mechanical advantage is 1. Now, when you find the ideal mechanical advantage with multiple pulleys or a bottom pulley, here's how you do it. You count the number of rope segments reaching up from the bottom pulley. If there's a rope going down from the pulley, it doesn't count. Only the rope segments reaching up will count. Include ropes that are tied to the bottom pulley and ropes that wrap around the bottom pulley, as long as they reach upward from the pulley, not downward. So here we count the 2 ropes reaching up, the 2 rope segments, and that gives you a mechanical advantage of 2. You can see from the diagram that the 10 newtons of force that this weight has are split between the 2 ropes. In this diagram, Here's one of your bottom pulleys, and there are 2 ropes leading up from it. Here's another bottom pulley. There are 2 ropes leading up from it, plus there is a rope tied to that bottom pulley. Therefore, there are 5 rope segments reaching upward from this bottom pulley, and this pulley makes it 5 times easier to lift the weight. In this example, there are 5 rope segments, once again, reaching upward from your bottom pulleys. So it is 5 times easier to lift this load with the pulley than lifting it just normally. You try 25 through 28. Finally, determine the ideal mechanical advantage of a wheel and axle. When you turn a wheel, you turn the wheel from the outside. So that is your effort distance. The inside, the axle, is the resistance. That is your resistance distance. Now, you just have to be careful because these either both have to be diameter or they both have to be radius. Right here we have one of each. This one's a radius, this one's a diameter. Let's convert them both to radius. Half of 12 centimeters would be a 6 centimeter radius. So you grab the wheel here, this is your effort, and the 6 centimeters goes on top. Then the resistance is the axle, and that radius is 1.5 centimeters. Then you just do your math, and you'll have your ideal mechanical advantage. You try number 30 and 31.